Okay, so off we go. Welcome everyone. I do have to say first thing, for legal reasons, I am recording this, and so while the radius of the microphone's pretty short, right, it probably won't pick up your voice, but that's always a possibility, and so just keep that in mind. If you ask a question or something, it might get picked up by the recording. Okay, so I'm not going to go through all this stuff again. Y'all have already seen the recording that I sent on Saturday, I guess it was, but I just feel it's appropriate for me to hit again this right here. This is really the big point, right? Make sure that you're approaching this course in the right way, right? So this is not a memorize and regurgitate kind of course. This is not a course where where you can just, kind of do it however you feel like it, and as long as you get the right answer at the bottom, that's all that matters. No, it's just not, right? So we are going to be, I'm repeating myself, but we are going to be looking for specifically your understanding of ideas and your ability to do valid mathematical reasoning, at a level appropriate to the course, of course. Okay, so again, I'm not going to repeat all that stuff, but I just wanted to remind you, make sure you come at this course in the right way, and with that said, let's move it along to the intro. So why are we here? Why are you taking a course in multivariable calculus? Some of you may be here out of just personal interest, and if so, that's awesome. But I think for most of you, you're here because your major requires it. Right, so let me rephrase the question. Why does your major require you to take multivariable calculus? So my starting point for this is this statement right here, which I'm pretty sure you'll probably buy. Single variable calculus is clearly very, very important. I know most of y'all are probably not math majors, and so the fact that it's foundational for math is, that's not a pitch for you, right? But for applications, the point is, derivatives are a way to get our hands on this really important idea of how stuff changes, right? The world's full of stuff changes. Stuff's changing all the time. Well, derivatives are how we write that down. And so, obviously, really, really important. Integrals, a lot of people misunderstand and think integrals are about area under a curve. I think that's inaccurate. Area under a curve is a convenient metaphor, I suppose, but it's really not the point, right? The real reason that integrals are super important in applications is because there are tons and tons of what I like to call accumulating quantities, stuff where the whole is the sum of parts. And there's just lots and lots of those in endless contexts. Integrals are one way of computing accumulating quantities. So, super important stuff. Okay, so why multivariable? It's a long list of reasons, but this is the easiest one to see. We live in a three-dimensional world, not a one-dimensional world, right? Dimensions correspond to variables. Right? The world's three dimensions in the sense that x, y, z, right? Three variables, three dimensions. Well, single variable would make sense if we lived in a one-dimensional world. So here are some kind of real quick sort of three-dimensional versions of questions that you've seen previously in one-dimensional context. So let's suppose, just to get it started, that temperature is a function of position, which, by the way, it is. Right now in this room, the temperature over there in the corner at the bottom of the floor is not the same as the temperature up there by that light bulb. It's just not. It's a little bit warmer by the light bulb, right? Probably by the window. So we have this multivariable function. Temperature depends on x and y and z in a weird way. There's a hot spot right in front of the projector lens, for example, right? And there's cold spots probably in various, but probably by the AC vents. Right? So highly nonlinear, highly weird function. And with that in mind, let's suppose that I'm here and I'm moving with that velocity. Notice, not in the x direction, not in the y direction, not in the z direction. I'm moving off at some weird angle, sort of, some random direction. And as I do so, reasonable question, how fast is the temperature changing? Well, single variable calculus is quite poor at being able to handle a question like this. It's not a single variable problem. We're looking at a function of several variables. So how do we deal with it? Well, answer multivariable calculus, and this is something we're going to talk about in great detail later on. But this is the kind of thing that we need multivariable calculus for. Here's another example. Let's talk about mass and density. Y'all have seen examples back in Calc 1 or 2 where you have a one-dimensional rod, perhaps, right? Or maybe you have a thing where when you take slices, the density in any given single slice depends only on x, right? That's a bunch of nonsense in most situations in the real world. What are the odds that density only depends on x? Very unlikely, right? Most of the time, density depends on all the variables, again, in nonlinear ways. If you give me a lump of stuff, there might be a heavy spot in the middle there somewhere, right? And so it depends on x, y, and z. Well, this idea that you can just take a slice, look at a thin slice of it, and then just claim on that thin slice that mass is density times volume? No, you can't. The density is not constant on that slice. Single variable calculus crashes and burns. Right, so here we are again. This is kind of like an old Calc 1, Calc 2 question, but it's Calc 1 and Calc 2 methods will not work. So how do we do it? Answer multivariable calculus. There's going to be a really clever kind of generalization of the idea of an integral that we'll do to address situations like this. So I hope that's a pretty easy pitch that because the world is 3 dimensions, 1 dimension is just not going to be good enough. You don't buy it? Now, to be clear, this is not the only reason that 1 dimension is not good enough. There is another good reason that we'll see in a couple minutes here. That 1 dimension is just not going to be good. In fact, 3 dimensions is not going to be good enough either. So let me come back to that in a moment. I want to show you some application-specific, in particular fields, applications that make sense just in those fields. So let's look at an econ example here. This is what you might call an economic model, and I just made this up. This is not a real, what are the odds? Probably not a real economic model. But this is kind of what economic models look like. You got a bunch of variables: price, quantity, interest rate, capital, labor, right? Stuff like that. And your economic model is typically not going to take the form of price equals the following function. Things just don't work out that nicely most of the time. So what you're probably going to have is some sort of an argument that says, okay, here's a bunch of stuff that's happening, and altogether we know that the combination of several parts of the problem have to cancel. All these things have to add up to 0, but those individual things might have completely different formulas. So an economic model very often will be either an equation or possibly several equations involving a whole bunch of different variables. Okay, so let's ask the question then. Let's suppose I start fiddling around with the values of 4 of those variables. Let's suppose maybe I increase L and I decrease K and I increase Q and I increase I at certain rates. Okay, well, wait a second. The equation's got to hold. If you just go around changing the values of the variables in an equation, the equation won't work anymore. unless you change the remaining variable in whatever way is necessary to kind of account for that, to kind of compensate for that, right? And so generically, under certain conditions that are satisfied most of the time, when you change certain of the variables, there will be a way to change the remaining variable to make the equation continue to balance. And so, natural next question then, given how you're changing those inputs, what can you say about the rate of change of the remaining variable? Well, single variable calculus is no good at this. Right? So this is going to be another question that multivariable calculus is going to help us address. Specific to economics. Does that make sense to everybody? Okay. Now, I want to point out, going back up to here, right? Clearly we need at least 3 dimensions per these examples, but here is my argument for why it's just not good enough to confine yourself to 3 dimensions. And the point is, those 3 dimensions might be position dimensions, but they might not be. Right? And you look at this example down here, right? How many variables are there? Well, there are kind of 6 variables in this example. We are doing math with 6 variables. We are doing math in a 6-dimensional space. It's super creepy when you first think about it that way. Everybody okay with that? And the point here is that the variables are just not necessarily going to be position, physical position. They just aren't. Right? So now, am I suggesting here that we're going to have to be able to visualize 6 dimensions and draw in 6 dimensions? Oh, no, definitely not. Nobody can do that. Nobody's brain works that way. We are intrinsically 3-dimensional critters. We have no chance of visualizing 6 dimensions. I have been able to con myself into maybe believing that by certain analogies and thinking about things in different ways and cross-check, maybe I can kind of sort of visualize 4. Not really. I'm kidding myself. I can't visualize 4 dimensions, and neither can you. Don't try. Right? So we're not going to be trying to do that geometrically, but we are going to be building up mathematical tools that will allow us to answer questions like this algebraically, because we 100% will need that. Okay, how we doing? Everybody happy? Okay, for the engineers and physicists in the crowd, some of y'all may recognize these equations. These are called Maxwell's equations. They describe a lot of how electricity and magnetism work. And if you've seen them before, cool. If you haven't, don't worry about it. We are going to make a lot of sense out of these equations later in the course. Not now. It's not tomorrow. Right? But coming up later in the course, we're going to be making a lot of study of these equations. And in particular, we're going to be asking questions like, what does that mean? All right, so there's a lot going on in that statement. What, for example, is that thing where I have 3 integral symbols right next to each other? What does that even mean? Right? So we need to know that. What does that mean? Well, we're going to have to make sense out of that. What does this mean? That's a weird look. If you take a close look at this thing, it looks like a differential. Sure, you've seen differentials before. This has an arrow over it. Have you ever seen a differential that was a vector? That's weird. So we need to understand what that means. And that's all multivariable calculus. This is all stuff that we're going to make sense out of in this course. Next, another reasonable question. In addition to understanding what that means, how should I think about that statement? It's one thing to know literally what that statement is saying, and it's quite another thing to have a point of view on how to think about that. Why is that statement true? We're not going to get rigorous with it, right? But why should it be true? Why does that make sense? Make it make sense, right? So that's something we're going to be worrying about in this class. And then furthermore, how does this statement help me understand electric fields? Well, it turns out that there's some really valuable things, really valuable points of view that you can make because of this statement, you can draw powerful conclusions about the nature of electric fields. And it's going to come out of understanding multivariable calculus conceptually, right? From a point of view of ideas and reasoning, like I harangued y'all over the weekend in that recording that I sent, right? Those points of view will help us understand the physical world in nice ways. Okay. All right. Okay. And then the last example I'm going to show you is from physics, arguably chemistry, depending on how you look at it. Let's take the chemistry point of view on this. If you're a chemistry major, possibly, you're going to have to understand molecular bonds. How do molecular bonds work? Well, they come from the behavior of electrons. What controls the behavior of electrons? Well, Schrodinger's equation. That's this right here. So if you're a chemist, then in some sense, at least at some level, you need to understand Schrodinger's equation. Schrodinger's equation, among other things, involves this operator, and that is an object of multivariable calculus. So this is, now we're not going to get into Schrodinger's equation in this class, but when those of you who take PChem do eventually get to Schrodinger's equation, multivariable calculus is going to be an essential part of being able to make sense out of it. And by the way, those of you who are physics majors, likewise. In fact, physics majors are going to do quite a bit more with this when you take a quantum mechanics class. And you'll be solving Schrodinger's equations in various scenarios and drawing really cool conclusions out of that. Okay. All right. Now, these examples field specific, chemistry, physics, econ, engineering, etc. Those field specific examples, I just picked the ones that I think are the coolest and the most interesting, most important, etc. It's not just that. This is not a complete list. There's bazillions more such applications. Multivariable calculus is everywhere in real world applications. So to answer my original rhetorical question, why do we need to study multivariable calculus? Well, it's because it's the calculus of the real world, which I think is a nice and pithy and importantly summarizing, again, why we're here. How we doing? Who's got a question for me? Anybody? Everybody's happy? All right. Okay, so that's why we're here. Now let's actually get into the material of the course. Chapter 1, it has a lot of review in it. A lot of Chapter 1 is linear algebra. Y'all have had a course in linear algebra. I know it's on the other side of a long summer, and you might have forgotten some of it. You might want to brush up, polish up your skills in linear algebra. We are going to use it a lot. I'm going to assume that y'all are good to go with a lot of linear algebra. Now, to be clear, I'm not going to do anything with Jordan canonical form, like I think I mentioned on the recording. So the far out, the weirdo, hardcore parts of the linear algebra, it's not going to come up, right? But you do need to be really good with the basics. And y'all will notice as we go, I think I enumerated some of the specific topics in the content syllabus. And y'all will notice as we go through certain topics of linear algebra going to come up. So you want to make sure that you polish up those skills super well. I'm going to start with section 1.6. By the way, I will bounce around through the content syllabus a little bit here and there. This is a great example. I'm going to do 1.6 before 1.1. Because I like to give myself, the tools of 1.6 I find convenient when I'm doing the content of 1.1, 1.2, 1.3, etc. So I'll do that in a few places throughout the course. Again, most of 1.6 is review, and I'm going to make y'all just review a lot of it on your own. I'll remind you, I have this sad duty to make tough choices as to what I spend class time on, right? And there's a lot of stuff at the end of this course that we really need time to dwell on. We need to be able to camp out and just focus on certain ideas because it's hard, it's new, it's challenging, and we really need the time. And reviewing linear algebra, by comparison, you don't really need me for that as much, right? And so a lot of the linear algebra review you're going to just do on your own. And so anyway, I'll be making a lot of these kind of tough choices, and I hate having to do it, but we just have to. Okay, so I am going to wave my hands very quickly at the triangle inequality. I think this is a pretty easy pitch. The triangle inequality is this inequality right here. And if you look at the picture, y'all know how to add vectors, right? A sum of two vectors is, you take the first vector and then you do the whole head to tail with the second vector, and there's your sum. And notice that this makes a triangle, and notice the magnitudes of these three vectors are the sides of that triangle. And notice, I think this is a pretty easy pitch, that if I were to look at that point, and if I were to ask what's the shortest distance between those 2 points, well, the shortest distance is the straight line, of course. Well, if the shortest distance is the straight line, then that means that this distance is less than the length of this other path, which is the sum of those other two distances. So I think it's a pretty easy pitch. Does everybody buy it? Yeah, good. Okay. Matrix multiplication. Now, I know you all know how to do matrix multiplication. I remind you, though, that the question, when you're thinking about matrix multiplication, the question is not which formula or algorithm allows me to compute that answer at the bottom of the page that I put into the box, right? The arithmetic of it all, not really what we care about. In practice, you're going to have computers do this stuff, right? So, the arithmetic, who cares? So, matrix vector products, the old, the dot product point of view, where you take the rows of A and then you dot those rows with the vector, and those give you the elements, everybody's seen. It's nice for arithmetic, but again, not what we're here for. This is a different point of view. I think this one's really well. They all have their moments. They all have their contexts in which they're useful. But there are a lot of situations where this is a much more valuable connection between different ideas. And so, just to focus, matrix vector product, like so, is a linear combination. Yeah, notice I'm not phrasing this as it's a vector of dot products. I'm saying it is a linear combination. It's a linear combination of specific vectors. It's a linear combination of the columns of the matrix. And what linear combination? Well, it's the linear combination that uses the coordinates of the vector as my coefficients. So this is the sort of the way you say it in English, and it's just kind of summarizing this equation right here. So it's a really nice point of view. There are situations where, again, you're not just interested in what is the resulting vector, but you might be interested in relating the matrix vector product to column vectors. And so maybe you know cool information about the column vectors. Well, this then allows you to take what you know about column vectors and relate that to the matrix vector product. So in really useful ways, this can be much more valuable than that dot product point. Nice fact. I want to make sure everybody's seen this, and in particular, even though computationally I know this isn't really the most efficient, doesn't feel like it's the most efficient way to do it, conceptually, if I had to pick a single point of view on matrix vector multiplication, this would be it. This is my personal favorite. My desert island matrix vector product point of view. It's this right here. Okay. How are we doing? Okay, linearity. Now again, I know y'all have seen this in the past, but it is something I've noticed over the years, over many years, is that even though students come into this class or other classes who have had linear algebra, I know they've seen the definition of linearity. A surprising number of students kind of forgotten the definition of linearity. Right, so this is something you got to make sure that you know. Here it is. Linearity means this right here, or pick your favorite equivalent formulation. These three different formulations are all equivalent, and they have their moments here and there. One might be the more convenient in one context, et cetera, et cetera. But just to keep it simple, I like number one the best. And there's different ways to think about it. I like to think of it as when you do a linear combination of inputs to the function, the output is that same linear combination of the outputs from the function. So you can do the linear combination before the function or after the function. Take your pick. Same thing either way. I think that's a nice point. Does that look familiar to everybody, I hope? Okay. So just to show you some examples, here are some statements about linearity. And starting with this first example right here, this function p is linear. A lot of times we'll say this a little bit casually, kind of a colloquial phrasing. We'll say dot products are linear, and I want to talk about why we would phrase this as such. Keep in mind we're talking about this function p, claiming that that's linear. Well, what does p do? P takes an input x, puts it right there. Now, what does p then actually do to the input? Well, it says right here in the formula what p does is it does a dot product with this vector a, whatever that constant vector a is, and the a has to be specified. So that's what p does. When we say p is linear, we're saying dot product with a fixed input on the left. Dot product is linear. Does that make sense? Yes?
Linear, is it the same as saying it's like a scalar result?
So there are linear functions where the output is a vector, right? So if you look back at the strict definition of linearity, and this is a narrow definition that I'm giving here. I'm assuming Euclidean inputs and Euclidean outputs. But the input can be any vector space, and those outputs, it doesn't have to be a scalar. Could be Rm, and in fact it could be any vector space. So there are lots of different sort of categories of linear transformation. Does that sound familiar? Okay, yeah. Great. Okay. All right, so how do you prove that dot products are linear in, this sense? How do you prove that? Well, you take this formula for this function and you plug it in to this statement of linearity. Compute the left, compute the right. Use what you already know about properties of dot products and just confirm that indeed this property holds, and therefore P is indeed linear. So that's a nice exercise. I want to encourage you all to make sure that you can do that. If you feel super confident that you can do that, it's fine. You don't have to actually write it down. It's not something that you'll submit, right? But this is a nice sort of warm-up kind of exercise. You want to make sure that you can do it. And so if you're not clear, then go ahead and take the time and actually write that out and persuade yourself that this is, in fact, true. And by the way, there is a homework exercise that's not too far off from this. So good warm-up for the homework. Okay. Pausing. Questions? All right, so a real quick comment, sort of a side comment. It is very common for my lecturing style when I'm teaching a class to throw out these, oh, hey, that'd be a nice exercise, right? And you don't have to do them, but what I have noticed looking back on things is that there is a little, it's not a perfect correlation, but there's a little bit of a correlation between when I say, hey, that's a nice exercise, and what end up being exam questions. And this is not on purpose. I don't do it on purpose, right? But it's just when I point out one of these things, it's because I think that's interesting, and because I think it's something you can reasonably do, and because I think it's a worthwhile exercise. And those features are actually pretty similar to what I'm looking for when I'm writing exam questions. So just kind of, it's an insight into how I write exam questions sometimes. So if you aren't persuaded to do it because it's intellectually useful, maybe you'll do it because it's tracks with good odds as possibly being insight into the exam. All right. Another cool fact. Another cool fact. Cross product is linear. And I'm going to basically just wave my hands at this one. You'll notice I deliberately wrote out the first and second examples there very, very similarly. In fact, I probably did a copy-paste. No, I guess not quite. But anyway, very similar statements. Yeah, I think I did actually. Look at this. I think that's exactly the same handwriting there, right? So very, very similar statements. This one's about the cross product. Again, colloquially, we'll say cross products are linear, interpreted suitably. Okay. All right, so again, good exercise. Now, this next one is weird and a little surprising, and it doesn't even seem right. It seems to be about this thing called D. D kind of appears to be determinant. Are we saying that determinant is linear? Why, no, not at all. Determinant is not linear, which is also not what this is saying, right? But just to be clear, determinant is not linear because, after all, determinant is a function that takes as its input an entire matrix. And if you take two matrices and add them, their determinants do not add. So determinant's definitely not linear. But again, not what this is saying. What this is saying is that this thing called D is linear. Now let's take a careful moment here to think about what D does. D takes a vector X, puts it right here, and then what does D do to it? Well, according to the formula here, D does, this. D takes all of these given constant vectors there, it stacks them up on top of X in order to make what ends up being a square matrix, and then takes the determinant of that. Right? So D is much more than just determinant. D says... D does not take a matrix as its input, just for starters. D takes a vector, makes a matrix in this weird way, always using the same constant list of vectors, and then takes a determinant. So this is actually linear. So proving this is a little tedious, but this might... you might recognize some similar statements. Do you all remember the relationship between determinant and row operations? Y'all may recall. Well, if you take those statements about determinant and row operations, and if you write those down, being careful with your notation, what you'll find is that those statements are actually a lot like this right here. And in fact, those statements about the relationship between determinant and row operations, they all follow from this. They all follow from the fact that that functions like this are linear. And I only wrote this, from the point of view of the last row, but it's also true with any one of the rows, and it's also true of any one of the columns. So even though determinant is not linear, there are these kind of different ways to interpret determinant as being functions of just one row at a time or just one column at a time, and those are all linear. This is called the multilinearity of determinant. Yeah.
Sorry, could you please repeat why D is linear and the process of thinking about why D is linear?
Why this is linear? Yeah, no, I never actually said why. Yeah, proving this is a little bit tedious, and it involves. I don't want to go down that bunny hole. Basically, it's too much trouble. So I'm just going to assert that it's linear, and yeah, that's all. Yeah. Anybody else? Okay. All right. So anyway, again, the goal here is not to understand multilinearity, although multilinearity is a very important, very cool fact of linear algebra, but just that there is this idea of linearity, and it manifests with certain kinds of functions, and these are just some cool examples. Okay. All right, here's another really important fact. This theorem right here. Loosely speaking, linear transformations are matrices. I think that's a really nice way to say it. I like it when stuff rolls off the tongue in a nice, pithy, satisfying sort of way. Linear transformations are matrices. Now, I'm deliberately sweeping a point under the rug here. When I say linear transformations are matrices, I'm only talking about Euclidean linear transformations. So specifically only functions from Rn to Rm. That's it. And when I say that they are matrices, what I mean is that if you turn the matrix into a function by way of this formula, then you will get that same linear transformation. So details matter, right? But interpreted with these qualifications, linear transformations are matrices. A really important fact. I hope you all remember this from linear algebra, right? Yeah. All right. How do we know this is true? This is a really cool proof. This is one of my favorite proofs in all of linear algebra. It's not hard. That's the point. It's one of the things I like about it, right? But it all follows out of a single clever choice. And I'm just going to go right to the point here. This is the clever choice. And I don't know who was the first person to think this through and to figure that out, but this is the brilliant thing that makes it all come together. If you just choose to make your matrix in such a way that the columns are computed by this formula, everything just works out. And specifically, let's talk about this formula. Notice that this formula says that we're going to take the standard basis vectors, and I hope you all remember standard basis vectors. So these are like ijk, right? If you're in 3 dimensions, a lot of people like to say ijk. They're, unit vectors along the coordinate axes, right? 1s and 0s, right? Take those standard basis vectors, apply the linear transformation to them, and whatever you get, make those the columns of your matrix. That's the move. That's the brilliant little idea. And if you make that choice, everything just works out. And specifically here, notice what I need. The feature that I need of this matrix is I need T of x to equal to AX, and check it out. It is. T of x is AX. And I'm going to let y'all read that algebra. Y'all have probably seen that before. You've seen something equivalent, certainly, at some point in the past. So think it through. Make sure you understand the details. Therein lies the devil and all that, right? So very important to think that through. But the point, the thing that makes it work is this right here. The columns of the magic matrix that works, the columns are the images, namely what comes out of the linear transformation, the images of the standard basis vectors. And this is the pithy little phrase that you should have deeply memorized. The columns are the images of the standard basis vectors. That's a tremendous amount of linear algebra in one little phrase. The columns are the images of the standard basis vectors. Does that sound familiar, I hope? Okay. All right. Okay, so in practice, how are y'all going to use this? How does this, what can you do with it? What can you produce with this? And here's the idea, one of the big ideas anyway. Let's suppose that you want to find the matrix that executes a certain linear transformation. Let's suppose we want to, let's say, rotate around the origin by some angle, 30 degrees, right, counterclockwise around the origin in the plane. How do you rotate some arbitrary vector 30 degrees, right, counterclockwise around the origin? Good. Well, I claim there's a matrix that does it. If you want to find that matrix, nothing to it. Take your standard basis vectors, 1s and 0s, no problem. Take those standard basis vectors, apply the linear transformation to them. Rotate them, for example, 30 degrees counterclockwise around the origin. Do a little bit of geometry and trig, and what you will find are certain results. Make those your columns, bam, you're done. There's your matrix. Magic matrix that will then rotate any vector 30 degrees counterclockwise around the origin. Everybody see how that works? Real cool trick. Real cool trick. Okay. All right. So now I'm going to remind y'all / point out. If I can get this thing to cooperate. There we go. I know that in when I give a lecture, I know I move fast, right? So, and this is a review, so we move real quickly through that. So, if you didn't quite digest all of that, no problem. You've got plenty of opportunities to get help on that, and so I'm just going to enumerate a few of these possibilities. Obviously, you can ask your friends. Right? Anyone else in the class, they need to know as well, right? So if you ask a friend, either they know and can tell you, in which case, cool, right? Win, right? Or they don't know, and now you have a collaborator in your hunt for the answer, right? Of how does this stuff work? So ask a friend. I think that's a good first step. Don't forget about the help room. The help room is there for y'all. No appointment necessary. Show up according to the schedule. Get help. It's all free. Right? It's a fantastic resource. I hope y'all will capitalize on that. And then, of course, there's also my office hours. You're extremely welcome. Come to my office hours. And I expect every semester a certain number of students to come in and say, yeah, that whole business about the matrices and the linear transformations and how do you make a rotation matrix? Yeah, I didn't get that. Right? So help, right? Totally no problem. Come on into office hours. I'll walk you through some examples. We'll do the geometry. We'll do the trig. I want everybody to make sure that they're good to go on that kind of stuff. So come on in, and I'll be happy to help. All right. Oh, and I can't remember if I said this already. I have a reciprocal agreement. Well, the course has a reciprocal agreement with all instructors that we share office hours. So y'all are welcome to my office hours, obviously, but you're also welcome at the other professor's office hours. So if the schedule for his hours works better for you, cool. He's a good guy. right? Go talk to him too. It's fine. You're totally welcome at that as well. Okay. All right. Last thing I'm going to say about linear algebra, for the moment anyway, is this theorem right here. I think this is underappreciated. It's about matrix multiplication. I know y'all know how to do matrix multiplication. Weird little formula with dot products. Not that different from matrix vector multiplication. Certain rows dot certain columns give you certain elements of the product. I don't know about you, but when I first saw that formula, I thought, okay, that's super weird. Why is that the formula? Why are we doing that? Right? It's a pretty reasonable question. Did somebody just decide that, and then we're all just kind of copying that guy? Right? No, I mean, certainly not. Right? There's a really good reason why that's the formula for matrix multiplication. I was not told this immediately when I first started learning this kind of linear algebra. Here's the reason. Every matrix we've already discussed represents a linear transformation like so. And when you take two matrices and multiply them, that corresponds to taking those two corresponding linear transformations and composing them. Again, in the same sense that the product matrix corresponds in the usual way with that composition function. So, this weirdo formula, why do we use this weirdo formula for matrix multiplication? Well, because that's what you have to do to make matrix multiplication correspond to this very natural mathematical process, right? Composition's supernatural. You're just plugging the Legos into each other, right? What comes out of the one goes into the next. It's just like Legos. Supernatural. Matrix multiplication is therefore correspondingly natural because it corresponds. Everybody buy it? That's a really neat fact, underappreciated. And when I first learned this, I was like, that's why did nobody tell me this before, right? This was a revelation to me a long time ago, of course, but really important to know. Okay. All right. Couple of quickie things. By the way, that does it for section 1.6. I have 3 minutes left in which I'm going to cover all of 1.1 by skipping most of it. Right? Again, y'all get to read most of it. I do want to point out that our book uses bold to indicate that a letter represents a vector. I think that's annoying. Right? Because with a pen or a stylus or a pencil, what are you going to do? Sit here and just do like that for 7 or 8 seconds? No, that's annoying, right? So the much more convenient way to do it is to use the little vector hat like that. I'm sure you've seen. I find this much more convenient with handwriting, so I'm unbothered by when textbooks use bold. But that's anyway. That's what we got. The other little notational point I want to mention is how to represent this vector between 2 points, P1 and P2. And of course, P1, P2, like so, is a natural thing to write. I'll point out, though, that P2, being a point, corresponds naturally to a vector. P1, being a point, corresponds naturally to a vector. And this thing that goes from P1 to P2, check it out, it plus P1 gives you P2, so in fact it is P2 minus P1. So this is an alternative way to draw, to algebraically write the same vector. So let's look at our two options then. For representing that purple vector, should I write it as this, or should I write it like that? And at the cost of an entire extra stroke of the pen here, you get something really valuable. And that is you get to see the algebra. Algebra is good. Algebra is our friend. Algebra is how we solve problems. We like algebra, right? Don't hide the algebra. That's my take. I mean, this isn't I'm not imposing a rule on y'all or anything, right? If you want to write it like this, okay, go ahead. But I like to see the algebra because I plan to use the algebra, and if I'm going to use it, I can't use it if I don't see it. So I always write it like this, and I encourage you to consider doing the same. And that's a great place to draw the line, and we will pick up here on Wednesday. Y'all have a good rest of your day. See you later.
Thank you.
Yeah, pleasure. Yeah.